All right, so in this video, I'm going to show you how to use integration by parts to evaluate an indefinite integral, and then I'll show you another technique that you can use that actually makes things a little bit faster, that is called tabular integration. So let's start with integration by parts. If I can get my pen to work, let's see. Smiley face to start us out. There we go. Okay, so integration by parts requires two parts to an integral. Okay. Here would be an example. Let's find the integral of x times the sine of x dx. Going through my integration checklist, the first thing I would probably try is to see if there's some function that has a derivative of x sine x, and I don't know one off the top of my head, so that doesn't work. If I tried to do a u substitution, maybe I'd first start by letting u equal x, then du would equal dx. Problem is I still have the sine of x left over. That's hard to get rid of, so that fails. Maybe instead, when you're trying this out for the first time, you let u equal the sine of x. Then du would be cosine x dx. Uh-oh, that's a problem. What's left over is x dx. I still have this cosine function as part of my du. So clearly a u substitution doesn't work. There's no fractions involved. So my inverse trig integrals are out of the way, or out of the picture. Partial fraction decomposition is out. Completing the square is out. What I'm left with is a method called integration by parts. And what integration by parts says is that the integral of u times whatever is left over, which we'll call dv, is going to be equal to u times v minus the integral of v times du. The way I remember it is ultraviolet voodoo. I don't even know what that means, but it's a nice, simple, silly way to remember. The integral of u dv is equal to u times v minus the integral of v du. The goal is that this integral is fairly challenging to compute right off the get-go, but the one on the right-hand side should be a little bit easier to work with. So how do you choose your u and how do you choose your dv? That's probably the most challenging part of the whole problem. I like to use the acronym LIPIT, where L stands for logarithmic functions, I stands for inverse trig functions like arctan, arcsine, arccosine. P stands for polynomials or algebraic functions. E stands for exponential functions, and T stands for trig functions, your typical sine, cos, and tan, or secant, cosecant, cotangent. Okay, what does the acronym mean? It's trying to give you a way to choose u. Best choices of u happen over by the logs and the inverse trigs and the polynomials, all the way down to your worst choice of u would be anything exponential or trig related. If you have exponentials or trig, those are typically equally bad. Okay, so you want to try to see if there's a logarithm, an inverse trig function, or a polynomial somewhere in your integrand, in which case that would be a good choice of u. The leftover part becomes your dv. So in this problem, I see my two parts that I'm looking at are an x and a sine of x. The x falls under the polynomial category and the sine of x falls under the trig category. So based on my little acronym to help me, I'm going to let my u equal x. Therefore, I'm going to let my dv equal the remaining part. That's why we call it integration by parts. Sine of x dx. According to my rule, I need u times v minus the integral of v du. So I am going to need a du. If u is equal to x, that means that du would equal dx. If dv is equal to sine x dx, to get from dv to v, I would take the antiderivative. The antiderivative of sine would be negative cosine of x. I'm not going to put the plus c right now because the plus c is going to come at the very end of the problem. Okay, so what we get is that x times the sine of x dx, uv minus integral v du. So pairing them up, u times v would be these two. X times negative cosine x would be negative x cosine x minus the integral of v negative cosine x times du. We had that du was dx. I'm going to take my two negative signs and make it a positive. So I get negative x cosine x plus the integral of cosine x dx. Like I mentioned at the beginning, this was a fairly challenging integrand to start with. Taking a look at what we have on the right-hand side, this is a fairly easy function to take the indefinite integral of. So we've simplified the problem quite a bit using this technique. negative x cosine x. The integral of cosine would be sine, since sine's derivative is cosine. Don't forget your plus c, since this was an indefinite integral, and that's it. A good way to check your work would be take the derivative of what I just put in the box, and you should end up with x times the sine of x. Okay, so that is called integration by parts. Now, another way to do that problem is using a strategy called tabular integration. I'm actually going to up the power of x just by 1 to show you why it's so nice. So let's do x squared sine of x dx. This also would lend itself to integration by parts. You could easily do this again with IBP. The problem is what's going to happen is halfway through the problem, the integral that we had on the right-hand side, let me point them out, this one right here, is going to end up involving something that needs another round of integration by parts. So to kind of show you what I mean by that, if you let u, in this case, if we use our acronym LIPET, I would let my u equal the polynomial, in this case, x squared. Therefore, my dv would be sine x dx. du in this case would be 2x dx, and v would be negative cosine again. So it starts out relatively the same way. uv minus integral v du. So this is where you'll see it turns a little bit trickier. U times v would be negative x squared cosine x minus the integral of v du would be minus cosine x times 2x dx. So you get negative x squared cosine x plus 2x cosine x dx. Here's where I want you to focus, right here. That's another IBP. That's another integration by parts. You would have to go through the process again within the integration by parts that you're already doing and use your acronym again. U would be 2x, dv would be cosine x dx, du would be 2 dx, v would be sine x. And this is starting to look like a huge pain because you're going to have to keep track of lots of negatives, lots of parentheses. It'll work. But alternatively, whenever you have an algebraic function being multiplied by some other type of function, whether it be an exponential, a trigonometric function, you can use a strategy called tabular integration. And I want to show you how that works on this problem because it's going to speed up this calculation quite a bit. It works whenever you have an algebraic function being multiplied by some other type of function like sine, cosine, tan, e to the x, some type of, I would say some type of transcendental function would be the best way to phrase it. So x squared, let's do this from scratch, using tabular integration. The choosing of u and dv works very much the same way. So you can still use your acronym LIPET to choose your u and choose your dv. So I'm going to let my u equal the polynomial x squared. I'm going to let my dv equal the trig function, sine x dx. Here's how tabular integration works. In the left column, you are going to take derivatives of what you chose for u until you get to 0. So the left column, I'm going to call the d dx column. You're going to take derivatives. So if I do that, if I take the derivative of x squared, I would get 2x. I would take the derivative again. The derivative of 2x would be 2. I'm going to take the derivative again until I get to 0. The derivative of 2 would be 0. And now I'm done with that column because I've reached my constant of 0. That's when you always stop, is once you reach 0. It's another reason why you need a polynomial or an algebraic function, is because otherwise you're never going to end up taking a derivative until it gets to 0. So it's important when you're using this that you have some type of polynomial. In the right column, what you're going to do is you are going to take antiderivatives or indefinite integrals of your dv. So if I integrate sine x dx, I would get negative cosine x. If I integrate negative cosine x, I would get negative sine x. And I need to do it one more time since I had 4 rows going on here. If I integrate negative sine of x, I would get cosine of x. And then I stop. As many entries as I have on the left, I want to have on the right. And what I create, I'm going to create diagonals with my top left element here. So x squared, I'm going to pair up with negative cosine x. 2x, I'm going to pair up with negative sine x. And 2, I'm going to pair up with cosine x. These are going to turn into products. And the products alternate sign. So my first one's going to be keep the sign positive. My next one's going to be negative. My next one's going to be positive. If the process kept going, it would keep alternating. Positive, negative, positive, negative. And what happens is I take products. It kind of looks like a little table, which is why it's called tabular integration. So this right here, my integral of x squared sine x would be equal to, my first product would be x squared times negative cosine x. So negative x squared cosine x. Minus, so this is where the sign changes. My next product would be 2x times negative sine x. So that's going to turn into plus 2x sine x. Back to positive, plus my last product would be 2 times cosine x. And don't forget your plus c. And I know I'm done because now I've reached 0. If I was to keep the process going, I would just be multiplying products involving 0. Put your plus c. And this is what would have resulted had we done the, I'll call it the nested integration by parts. You would have gotten the same result, but it takes a lot longer to get there. The benefit of this strategy is no matter how big the power is on x, you could do x to the 5th. It's a lot faster to do 4 or 5 rounds of tabular than it is to do 4 or 5 rounds of integration by parts. Now, if you're looking for a good summer activity, try it. Okay, hopefully this helped see how those two strategies work. Happy mathing.